Today we're going to have the fifth and final video in the series, and we're going to discuss specifically how we use the magnetometer to configure a survey to find a target of a given size, and then that will inform us about the line spacing for our survey grid. I want to go over a couple of other points that need perhaps a little more explanation regarding the rules of thumb that I discussed in the past. The first one is that 1 ton of ferrous material equals 1 nanotesla at 100 feet. Now you'll remember that this is the induced formula to give us the size of anomalies that we get from various targets. In the interest of being worldwide with our discussion here, I want to say that 1 ton is equal to approximately 900 kg. And besides a nanotesla, we can also use the terminology gamma. This is an older term, but one that's still used. It's equal to a nanotesla. And of course, 30 feet would be 30 meters. So 900 kg, 1 gamma or nanotesla at 30 meters. And then of course, as we lower the range, in other words, if we went to 15 meters, we would still see the 1 nanotesla or 1 gamma, and the mass would then go down by a factor of 8. So we would see approximately 110 kilograms would give us a 1 nanotesla at 15 meters. And just to finish this out, 1 gamma at 7.5 meters, 8 goes in here approximately 14 times. So now we would see 14 kilograms at 7.5 meters. So we can see again, we can see a very small target at quite a large range. The other thing I wanted to mention here had to do with the angle of the Earth's field, and we were discussing that these anomalies typically take on the form of a sombrero, where this is the high and this is the low, and the object is actually here. If we were to extract a line, a survey line with our magnetometer, this is a plan view of the anomaly. If we were to extract a survey line through the anomaly, what we would see is, here's the anomaly, and we would see a high to the south. We would go through an inflection point where the object is, and then we would see a low to the north. I wanted to point out, however, so this is the high, the low, and this is where the object is. I wanted to point out, however, that this is only for the northern hemisphere. This would be reversed in the southern hemisphere. So to be cosmopolitan here and talk about these surveys that are done in the southern hemisphere, this would be reversed. So again, let's draw that again. If this is the north and this is the south, and we're in the southern hemisphere, and we extract this line, first of all, our anomaly would be the other direction. So we would expect to see an anomaly pattern like this. And so what we would see is we would see a low to the south and a high to the north, and the object would be here. So we would see a low to the south and a high to the north, and this would be in the southern hemisphere. So all of the discussions that we had regarding the shape of the anomalies, this is north, this is south, are flipped for the southern hemisphere. Just want to make that point. Okay, so let's go again talking about how far we can see objects. I'm going to use feet and nanotesla. Remember our chart and the summary we did previously, which was that 1 ton, 1 nanotesla at 100 feet. But that we have some multipliers. We could take this down to 250 pounds. We could take this down to 32 pounds. We could take this down to 4 pounds. 1 nanotesla, 1 nanotesla, 1 nanotesla. And these distances would halve. So 50 feet, 25 feet, 12 feet. Now, remember though that we have multipliers, and our this is purely induced. We have multipliers. We have permanent magnetic effect. The perm can add perhaps 3 to 5. We have hollow. Again, the hollowness of the object can add 2 to 3. And then we have aspect ratio. And the aspect ratio again means that the object is longer than its diameter. It looks like something that would fly through the air or the water, for instance. And that can also increase at a factor of 2. So when we actually design the survey to find a given object, we can take a couple of different tacks on this. We can, for instance, go with the most conservative estimate. The conservative estimate would then say that we don't take these factors into consideration. And when we make our line spacing or consider how deep we should tow the magnetometer in the water, we would actually say that probably somewhere around 1 nanotesla would be our limits of detectability. Now the magnetometer can see perhaps 20 to 50 times better than that. It can see its own noise level is 20 times lower than this. But there are a number of other factors that are adding into the noise that are not from the system itself, but are from the Earth. And they include micropulsations, which are momentary disruptions in the Earth's magnetic field, perturbations due to the charged particle flux from the sun. They have to do with magnetotelluric currents that are running in the Earth. They have to do with electrojet. There's a high current electric field flow in the ionosphere, which can generate some momentary disruptions to the Earth's magnetic field. And there are waves. These are sea waves. These are conductive water waves which have the ability to generate small eddy currents as they move through the Earth's magnetic field. So all of these generate some noise, and they are external to the magnetometer and being measured by the magnetometer, and they are not coherent, meaning that they do not repeat normally in a way that we could say filter them out. So what we would want to do is probably set a lower limit of 1 nanotesla. So how this informs our survey is that, let's say, for instance, and we'll just take an example here, that we want to be looking for 250 pounds or approximately 100 kg of ferrous material. And so now we'll sort of design a survey around that. And then we'll use these perm and hollow and aspect ratio numbers to give us an idea of what kind of anomalies we might expect from that 250 pounds. So we'll put this back up. 250 pounds equals 1 nanotesla at 50 feet. So that means that we could have a survey line. If we can see 50 feet on either side, we could have that survey line 100 feet wide. So this means that on any given survey line, we will be able to see out 50 feet.